Okay, so in this lecture we look at some generalizations of ideas we have seen. So we have so far restricted our closed contours to be simple, and these contours could not cross themselves. But in this lecture we will see how these ideas can be generalized to allow for contours which are crossing contours. When we're looking at what is called a simply connected domain, right? And we will also look at what happens when a multiply connected domain is introduced, and how the Cauchy-Goursat theorem plays out in a multiply connected domain as well. Okay, so what is a simple contour? A simple contour is a contour which does not basically cross itself, right? So uh, it so happens that the Cauchy-Goursat theorem, it also holds for non-simple contours provided you're in a simply connected domain. So what is a simply connected domain? So a simply connected domain is one in which every simply closed contour encloses points that are also in it, right? So if you take a simply closed contour and look at all the points inside, every point inside which is enclosed by a simply closed contour is also part of the domain, right? So in other words, there are no disconnected portions in your domain. You can take any closed contour and keep on shrinking it, and you will always remain within your domain. So that's the idea of a simply connected domain, right? So domain is like the whole region that is under consideration, and contour is like something which you specifically consider inside the domain, right? So a simply connected domain is one in which every simply closed contour basically encloses points which are all necessarily inside your domain, right? So we look at what a multiply connected domain is, and then the idea of a simply connected domain will also become clear. So if a function f of z is analytic throughout a simply connected domain, then the Cauchy-Goursat theorem holds, right? Even for non-simple closed contours, right? So what is a non-simple closed contour? It's something which looks like this. I have a very sort of schematic diagram of a non-simple closed contour. It's basically a contour which can cross, and it can cross many times. I have drawn it, to illustrate just one crossing, but you can have more complicated non-simple closed contours, and basically Cauchy's theorem will still hold if you're considering an integral of this kind f of z dz over this entire path, so that this contour entire c can be thought of as, if suppose you start with a, you go to the point d, come down to b, and then come back to a, and then you go along f, or you go along so suppose you start from here a b d a, and then you can come down a e f a, right? So this is one kind of a path which has to be defined carefully, right? So suppose this is what C is, then you can actually think of this as being made up of two simply connected simple closed contours, right? So you have a C1 and C2, so we can define C1 to be a b d a and C2 to be a e f a, right? So as far as your overall contour integral is concerned, it is made up of a sum of simple contour integrals over simple closed contours, and then the Cauchy-Goursat theorem holds individually for each of these bits. And so since individually these two are 0, this overall integral contour integral over this non-simple contour is also 0, right? So it's fairly straightforward. You can have more complicated non-simple contours, but your overall region is simply connected, right? So which means that there is no mess sitting in some region around in your region, and then this is always possible, right? So the best way to understand how this is a simply connected domain is to look at what the idea of a non simply connected domain or a multiply connected domain is. So let's look at what a multiply connected domain is, and then we'll immediately be clear with the idea of what a simply connected domain is. And how is a multiply connected domain defined? It's a domain which is not simply connected, right? So let's look at an example, and then you'll see how a multiply connected domain basically contains disconnected parts. So essentially not all closed paths, you cannot keep on shrinking them down to point while always remaining within the domain, right? So suppose we have a situation like here. So I am looking at a contour C1 and everything inside this contour is part of the domain except there is some this region. So in fact, so we have an annular region between concentric circles, or in this case it does not even have to be concentric circles. So there is some sort of mesh sitting in the center. So there is a non-analyticity here. So there is a I mean, for whatever reason you're considering the region which is annular to this, you're not allowing, you're not allowing this central region to be part of your domain, and such a domain is called a multiply connected domain, right? So if you consider a multiply connected domain of this, and it can even be just a single point. Suppose you take the entire complex plane but do not allow the origin to be a part of your domain, then that's going to be not a simply connected one, because if you consider circles around the origin and then keep on shrinking these circles in size, you will have to keep on excluding one part of it. So you cannot continuously shrink it, to point and to a point and allow it to be part of your domain. Everything inside your contour also must be part of your domain. That's not going to happen. So it's a multiply connected domain. Now, so you cannot apply the Cauchy-Goursat theorem blindly when you have mesh sitting in the center. So you, in particular, you cannot say that this contour integral C1 f of z dz is going to be 0, right? So one example we have seen is that of 1 over z squared dz, and you cannot blindly say that it's going to be 0 invoking the Cauchy-Goursat theorem, because you have, there is a singularity sitting at the origin. But we have seen that there is some other way to argue for that particular result, and that's why it's important to emphasize it. So that result may hold, but it's not a consequence of the Cauchy-Goursat theorem. Now let's see what happens with how can we still work with a multiply connected domain and still after all, this function is analytic in this entire region, in this annular region. So is there a way to come up with some other contour and still make use of the Cauchy-Goursat theorem, and what consequences does that have? So let's introduce what are called bridging contours. So you consider some in between contour, which I'm calling C2 here, and where the direction of motion is now clockwise. So you can think of this C1, which is this outer contour, and this C2 as this inner contour. And so suppose we consider this entire region which lies between C1 and C2. Now that can be your contour of interest, and so there of course your function is entirely analytic in this entire region. So you should be able to say that the sum of this f of z dz on C1 plus integral f of z dz C2 must be 0, right? In some sense you can think of this as your closed contour which entirely lies in an analytic region, and so therefore it should be 0. And there is a way to argue for this, and in a transparent way, and that is to use these bridging contours. So what you do is you think of this C1 plus C2 is basically you go along this. So you can think of C1 plus C2 as the same as C5 plus C6. We introduce these contours which will start with A, go down to B, A, B, D, E, F, G, and A, right? So this is 1. So this kind of a contour is 1, and then C6 is something like B, B, G, F, H, D, B, right? So you see that if I add this contour and if I add this contour B, G, F, B, G, F, D, B. So we see that when I sum these two, I'll find that in one of these cases I'm moving along this direction from B to D, and the other one I'm going from D to B. And likewise in one of them I'm going from G to H, and in the other one I'm going from F to G, G to F, and F to G. And these parts will cancel. Everywhere else, if you just carefully watch what is going on, it's nothing but going along C1 in the outer contour and going along C2 in the clockwise direction in the inner contour. So basically, and then we argue, of course, for this path A, B, D, E, F, G, A. So indeed the Cauchy-Goursat theorem must hold, because everything inside the function is analytic everywhere inside this region, and it's basically a simply connected region, and it's a simple contour. So it's going to be 0, and also in this region it's going to be 0. So overall, this sum of these two contours is indeed 0, right? So this is a direct consequence of the Cauchy-Goursat theorem. And there is an important corollary from this, which is also called as the principle of deformation of paths, right? So if you take C1 and C2 to be two positively oriented, right, anti-clockwise oriented simple closed contours, C1 is some outer one and C2 is some interior closed contour, and then if your function is analytic in this closed region consisting of those contours and all points between them, right? So we are not saying anything about this inner region. There could be mess in there. So what this the result pertaining to Cauchy-Goursat theorem for multiply connected domain implies is that the contour integral over C1 of f of z dz is the same as the contour integral C2 of f of z with respect to C2, right? So the reason is that whatever mess is there is hidden right in the center, right, which is interior to C2. So then it doesn't matter which contour you take, because the entire region between C1 and C2, it's analytic on the contour C1 and on the contour C2, and in the entire region between C1 and C2 your function is analytic. Therefore you can actually deform contours, right, as long as you don't cross any singularity, as long as you do not cross any non-analyticity. So now of course you notice also that the sense in which C1 moves is the same as the sense in which C2 moves. And this is a direct consequence of the previous result, right? After all, the previous result says that if you take this and then add it to minus C2, right? So here you see that the sense goes in the opposite direction when you're doing it as a plus this thing. But then you immediately argue that plus C2, in this case will be minus C2, because I put it in the different direction. So basically what it boils down to is that you can deform contours as long as you don't cross any non-analyticity when you're doing this, right? So this is also a result of great importance, and we will apply it as we go along as well. Let's look at an example. So we have seen that if you consider the function f of z is equal to 1 over z, it's analytic everywhere except at the origin. And if we consider this kind of an integral 1 over z dz over some contour c which goes around the origin, right, which does not have to be a circle, any contour which is in the positive sense must be the same as in the same sense if you take a different path, which we can take for simplicity to be a circle of radius r, but we have already evaluated this contour integral of 1 over z dz over c naught, and that we have found it to be 2 pi I. So thus we have the result that 1 over z dz over any closed contour in the positive sense which encloses the origin and does not go through the origin is the same, and that's going to be 2 pi I, right? Okay, so that's all for this lecture. Thank you.